Well, today we're going to talk about fluid statics. I'm guessing that the reason it's doing this is because this little equatio is open at the bottom, so which is a cool little graphing tool that we'll use today briefly. And so that kind of stops us doing this, but you get the rest of it otherwise. So obviously, the free diving stuff is kind of interesting. As you know, as you go down in the swimming pool, your ears potentially pop. You know, as you go up in an airplane, your ears potentially pop. It's due to the fact that pressure changes with elevation. And of course, we know that fluids, solids, weigh something, and the amount of stuff above you is really what's driving that behavior. So this is actually the Hillary step, I think, on Everest. So Everest, just short of 30,000 feet, 29,000 and change. And of course, as you go up there, this is the last big step before you get to the summit, apparently, that you have to overcome. But lots of people, when they go up to Everest, they use oxygen. And they use oxygen because the air is thin. These guys, look, yes, they've got masks on. Guys and gals, you can't tell. And it's because the air is relatively thin, because above them at 30,000 feet, there's not so much air, and therefore the pressure is lower. And therefore the pressure is lower, the concentration of oxygen, I don't know what that is in air, it's probably 90% nitrogen and 10% oxygen. The amount of oxygen available for your lungs is less. And so that's why often when you climb in these situations, you climb with oxygen. Apparently when you fly, I was reading the other day, the airplanes are pressurized to 6,000 feet equivalent. Happy Valley, we're at about 1,000 feet above sea level. We would have higher air pressure than Denver, the mile-high city, which is about 5,000 or 6,000 feet. So they're roughly the same as the pressurization at 6,000 feet. Planes fly at Everest height, 30,000 to 35,000 feet. And so if you do have a depressurization, that's when the little yellow face masks drop out for you. And hopefully it's not a catastrophic depressurization like a window blowing out, which potentially would suck some people out. Which is not a nice thing to really contemplate. Don't sit next to the windows in planes, perhaps. I'm not sure what the message is of that. And so that's in air. And so the pressure of 101 kPa that we feel here is because we have a certain amount of height, a column of air above us, which is held by gravity and therefore pushes down on us. The 101 is absolute pressure. We talked about that. We usually take that as zero pressure gauge, just out of convenience, because that's what we live at. But if you use, for instance, the ideal gas law, you have to use that correct amount. So what else is used here? So we're using this because, okay. The other thing that is relevant, so you must have seen all these tank cars, and they have this funky dog bone shape where they raise along their length. And so there's a reason for that, and that is to stop you popping the hatch off when the train accelerates. So these are oil cars. They're bringing, perhaps if you see them come through here, they're bringing oil from the Bakken in North Dakota across to markets in the east. And when you start a train, of course, it accelerates. And if you think of me running across the front of the room with an aquarium with fish in it, you could imagine that the surface of that aquarium would rise in the direction in which I'm pushing it across as I accelerate across the room. And you see exactly the same process here in a bus. This is a bus that has a double glazing. It's got some water between the double glazing. And as you see it accelerate and decelerate, the angle of the water in that gap, that air gap, is not meant to be a water gap, changes. So decelerating when it piles up to the front, and accelerating when it piles up from the back and is moving forwards. And so that's the kind of questions that we'll try and answer today, is looking at fluids as static materials, and where pressures at a point, the pressure that we feel here, depends on not just the properties of the fluid around us, but also the stuff above us, because gravity acts downwards, not so much the stuff below us, actually not at all the stuff below us, but the stuff that's stacked above us. So that's kind of where we're going here. So I realize that my don't know what the other stuff is. So that was my solution to the fact that this didn't work today for me. So I can get rid of that, I suppose. Okay. So, oh geez. Do I have to do this? Was it Safari? Might as well do this. Done. All right, we should be. Well, I guess I should see whether this will actually open up now. So, let's see. That's a good omen. So anyway, so if we look at what we talked about already, just by way of a recap, I don't want to do a long recap, but if you look at what we talked about on Friday, kind of summarizes many of the things that we talked about. And, well, we talked about a bunch of things, including wave speeds, viscosity, vapor pressure, and surface tension. But the things we might want to draw on today, which we didn't talk in any great detail about, was to talk about, I'll do it in red because I like red. Mass is equal to density times volume, you know that. Simple statics. And weight is equal to mass times gravity. So you know that. The other thing we'll draw on today is the ideal gas law. And we'll also use our concepts of compressibility or modulus to be able to decide on our way ahead. So we'll use those three concepts today to be able to round out our discussion on statics in fluids. Pressure at a point, in other words, if we want to define it. You'll notice that I don't go through my own notes. I prefer to write things down. That's just the way I do things often. Sometimes it makes sense to go through them. Today it doesn't make sense to go through it. So these are the three things that we'll talk about today. So we'd like to talk about fluid pressure at a point. And we've said before already that it relies on the material around us. We'll find out that this expression here, that the change in pressure with elevation is equal to negative density times gravity. So that's the definition of unit weight. We've talked about that. And we'll define why that's so, and then we'll talk about how the fluid change with elevation is different depending on whether we're talking about an incompressible fluid, such as water or an oil, a liquid, or whether we're talking about a compressible fluid, which would be a gas. So that's basically the idea. So the overall idea, I suppose, is that you can think of, if you want to define what pressure changes with elevation, again, I'll call this negative z. So we'll take z as positive upwards, and I'll talk about pressure. You could imagine that if you take a bucket of fluid, because people prefer perhaps thinking about buckets rather than differential volumes, that you could calculate that the weight of this is equal to the volume times the density times gravity. So this would be, these terms on the right-hand side, rho g, would be, velocity times density would be the mass, right? This term here. And if we have on top of here an area, then we can imagine that for this to be in equilibrium, what we'll call pressure 1, that pressure 1, or P1 is a force rather, let's call it a force, which is uppercase P, is equal to the pressure that's acting on this surface, lowercase p, I know you can't perhaps tell the difference, times the area. And this has to be equal to the weight, which has to be equal to the volume times rho g, which is also equal to z1 times area. So these two together are volume, right? This term here, times rho g. And so if we take out of that expression the two areas, so if we write this, P times A equals Z A rho G, get rid of the two areas, we have P is equal to rho G Z, which is equal to unit weight times Z. So unit weight is just the product of these two. And so if we go over here and we draw Z1 and P1, we have kind of a self-evident truth that you know to be true, and that is that this curve kind of goes through here to that point. So what we could also do now is we could take another bucket and put this bucket on top of that bucket and go through the same process to get Z2. And I guess you'd find out this is P1 perhaps. We'd find out that P2 is equal to P1 because the force pressure acting up here has to be acting down as well by equilibrium, plus rho G Z2. And this is Z2. And so you'd think from this that the pressure P2 we could write generically just as this expression here, kind of. So pressure is equal to unit weight times the height. We should think of perhaps Z as being equal to a height because I said before that we'll define Z in a very specific way as positive upwards. And so this is really a height that defines it. Defines it H1, which would be equal to Z1. And that's kind of part of the story. It's not a complete story, though. And the reason it's not a complete story is that if you believe me, and if you think of the Hillary step on Everest that we just talked about, Everest is something like 30,000 feet, which is about 10,000 meters, 10 kilometers, roughly. And so if we go up from here, where we find ourselves at, in terms of absolute pressure, sea level, if we could get to sea level. Obviously, base camp of the Himalayas is much above sea level. But if we go up from 10 to the 5 newtons per meter squared, which is atmospheric pressure, right? We called it 101 kPa. This is roughly that. And if we use this expression, then we'd expect by doing this bucket of air all the way up to the top, if the density of air is equal to, and again, if you believe me, 1 kilogram per cubic meter, it's roughly that, then P2, P Everest perhaps, would be equal to rho G H, which would equal to 1 kilogram per cubic meter. G is 9.81, let's take it 10 meters a second squared. This is 1 kilogram per cubic meter, and this is 10 to the 4. So this together gives us the pressure on top of Everest should be equal to 10 to the 5 pascals. And that's pretty good. But we know that if you're on the top of Everest, there is some air above you. Otherwise, you'd probably be using, you couldn't climb it. Some people do climb it without oxygen. So we know that's an oversimplification. And so the reason why that's off is that we treated the density of air to be 1 kilogram per cubic meter and constant all the way up. But we can imagine if there's a pressure that's compressing it, then we get up at a higher elevation where the pressure is less, it'll be less dense. And so that therein lies the rub for what we'll talk about. So that's why we need to be able to say something about, understand both compressible flow and incompressible flow and make the difference between them. So what we'll do is we'll talk about an accelerating fluid. And I made the case for the bus with the water in the air gap. And what I'd like to do is, let's see if this will. So I'm going to draw a picture on the left-hand side, and I'm going to use that picture to illustrate some math on the right-hand side. So what I want to draw is, instead of a bucket, I want to draw a differential cube, dx, dy, dz. And it's going to look like this. And I want to leave enough space to the right-hand side to be able to do the other things I want to do. And so this is, instead of our bucket of area A, still has many of the attributes. I'll draw a coordinate system attached to it. And that coordinate system is x, y, and z. The so-called right-hand coordinate system. Right hand because this is x and y. I should do it into the camera since we've got the FaceTime camera. X, y, and z. Z, as we said, is always upwards. The bird finger is always upwards. And then we can put some other components on this. So if we go in the x direction, we'll call that length of this side dx. We'll call this side dy. And we'll call this side dz. We'll draw some other things like a pressure acting upwards and a pressure acting downwards. So this is a little piece of a differential cube that would be the same as our bucket at the bottom, which has some stuff above it, maybe some stuff below it, some stuff on the left side, some stuff on the right side and behind it, etc. And we're going to define this as a pressure plus a small change in pressure. And we're going to multiply that pressure by 1. So dz over dz is equal to 1. Does this work? Yes, this. Oh, no, it doesn't work. I thought this was it. Yeah, this will work. See if this works. Oh, this is so skillful. I'm an artist. Well, it's not that skillful. I'm an artiste. So the area is the top. And of course, the area will be dx dy in this particular case. And we can define a couple of things. So one is we could define what we refer to as an acceleration. So you're taking this block of water and we're moving it upwards, not a constant velocity, but an acceleration. And we're taking this block of water and also acting downwards is its weight. So not very different from the bucket that we drew before, right? It had a self-weight. It had no pressure on the upper one, but had a pressure on the lower boundary. And do I need anything else? No, that's about it. And so you realize, of course, that multiplying dp by 1 is still just dp. So this is a small increment of pressure. We don't know whether that be an increase or a decrease. And so now what we'd like to do is we'd like to use Newton's second law. So I'm going to make this small now so I can get the whole thing in. Newton's second law is F equals ma. You know it's the sum of all these forces. And you also know it's a vector, right? So this Fx, and so this is really Fx equals mass times acceleration in the x direction. Fy equals mass times acceleration in the y direction. And Fz equals mass times acceleration in the z direction. Perhaps more math we need, but you know that this F here is really just a vector that we could put a bracket around like that. So we're doing that. So what we'd like to do is, first of all, let's take it and let's write it as sum of Fz, vertical direction, is equal to mass times acceleration in the z direction. And let's, instead of writing it that way, write it, of course this is sum of. Let's write it as sum of forces in the z direction minus mass times az is equal to 0. Right? That's fine as well. Right? And let's go back to this differential cube and start figuring out what those should be. Perhaps use something else. So the force is acting upwards. An area multiplied by pressure, positive upwards because it's in the positive z direction, minus p d plus dp goes here. What else do we have up and downwards? We have minus the weight. Weight is going to be equal to area times dz times rho g, right? Area times dz is just the volume, not divided by volume, but it is the volume. And so we could write that in as area dz rho g. G is already acting downwards. And we have an acceleration which we want to subtract from it. So this isn't a force anymore, but this is the acceleration. So this is a weight. The mass is equal to a weight, which is going to be area dz times rho az equals 0. And so my reason for doing that is that if I come down here, I want to show you that in this class we're not going to use ever anything much more complicated than F equals ma. And so these are the forces that are acting on this thing which are static, and this is the resistance to it moving, which is the inertial force, which is stopping its acceleration. And so what we could do, I suppose, is we could realize that this and this cancel. We could realize that, okay, we've missed out something here. Let me move that bracket back a little bit, I realize. In green. And this is, I guess I want to move it back twice. This is equal to multiplied by dz over dz, bracket, bracket. And so this dz goes with this, just like these do. And so we could multiply both sides by area times dz, which is volume, or I guess divide them. So divide by that, and we'd end up with minus this term here. That's it. We're there. That's all we need. And so what that is saying is that we have an expression that says when this will be an equilibrium, which needs to be an equilibrium. We know that we have 3 of these orthogonal resolutions that we could possibly make. We've made the most difficult one in the vertical direction because it includes gravity. But we could think about resolving it horizontally and in x and y. And if we do that, we'd end up with minus dp dy minus 0 minus rho ay equals 0. So ay, if you're curious, it would look like something like, no, not that. Would look something like this. So we're allowing it to be accelerated in any direction, and we'd end up with minus dp dx minus 0 minus rho ay is equal to 0. And so these are the three static equations. And of course, a static fluid which is accelerating seems like an oxymoronic term, right? A misnomer. How can you have a static fluid which is accelerating? Well, I guess the idea is that static fluid is within an aquarium. So it's not circulating inside the aquarium, it's just moving as an uncirculating fluid and accelerating across the front of the auditorium or accelerating upwards in an elevator or doing something. And if we do that, then these are the equations of the pressure changes that we have within that fluid. And so we won't worry. Go ahead.
Is it supposed to be rho ay for the x term?
Yes, it is. Thank you. On the ball. Great. AZ, AX, right?
Yeah.
Yeah. Yes, thank you. So this defines exactly the behavior of our system. And for our uses today, what we will do is we'll use this again. We'll use it for the idea of this bus accelerating and having the elevation of the free surface in the air gap being inclined. And we'll also use it to define Bernoulli's equation, because even though it's a static equation, we can use it directly to define Bernoulli's equation, because Bernoulli's equation is just a manifestation of F equals ma. So what we'll do to make our lives a bit easier is that we'll note that for now, let's assume that ax equals ay equals az equals 0. No, I didn't mean that. And if we do that, what do we get? Well, these terms all cancel out. They go to 0. And we're left with dp dz equals minus unit weight, right? Rho y is unit weight. And we have dp dy equals dp dx equals 0. So we did the hard graph to do this so we don't have to do it again, but this is all we want to use. Of course, you recognize something here because this is exactly this, right? This expression, which we want. And it also seems a bit strange what these expressions are, but we've actually used this already. You might remember our closing breath last time was looking at a capillary tube. And what we said was that if we have a capillary tube with a fluid within it, we know that this point here is at atmospheric pressure, which we can take as gate pressure 0. We know if we go horizontally along any surface, we end up at this point here, and the pressure also has to be 0. And so what we can do is we can cut off a free body that looks like this. And we can just look at the weight of this minus the forces that are applied on the circumference of this as you go. So we've already used this. So this is z. This is x or y. And this is z. And so this is saying as we go horizontally that the pressure doesn't change. And so by definition, we're going horizontally, but we're going around this little break. We're getting to this point without going outside the fluid, and therefore the pressures have to be equal to 0. And so we've used that already. So now we'd like to use this to be able to say something about how we can define pressures as we go up or down. And so we've made the point that it's different when we look at an incompressible fluid. So I guess an incompressible fluid will be where density, change in density with pressure is equal to 0. And a compressible fluid is where change in density with pressure is not equal to 0. In fact, it's going to be equal to, pressure is equal to rho RT. Right? That's what we've used for gas. And so that's what we're going to do. And we've done the heavy lifting already, so it should be pretty straightforward to do that. So for incompressible fluid, okay, what do we got? We've got dP dz is equal to minus gamma. The minus, by the way, is directly because we've drawn our coordinate system vertically positive upwards from our right-handed coordinate system. Always will do that. And so if we want to be able to figure out exactly how pressure changes as a function of depth, pressure as a function of depth minus z, then what do? Well, we can write that dP is equal to minus unit weight times dz. We can take an integral of that. We can evaluate between P1 and P2, Z1 and Z2. So and what would it look like? I guess it's going to look like this. This would be P2 and this would be P1. And you all know how to do this. It's going to be pressure evaluated at P2, P1 equals minus unit weight elevation evaluated at Z2, Z1, which is equal to P2 minus P1. It's not going to be very different from what we've had before. Z2 minus Z1, which is the same as P2 is equal to P1 minus unit weight Z2 minus Z1. So maybe a bit cumbersome mathematically, but you've kind of seen this before. If we go up to here, this expression is kind of like that. The only thing that's changed is that we now have a negative because we've defined z differently. Z was just the positive depth, really the height. We should probably think of this as just a height rather than z. But if we use this sign convention, we end up with this is the change in elevation between these 2 points, and the difference will be equal to the pressure at this point here minus the height of these, because Z2 is bigger than Z1. This will be a positive number. And so as we go upwards, the pressure will be less. Going up Everest, going up in a plane, we're losing altitude. And so typically, I would imagine that you'd probably want to write something like P2 is equal to P1 plus unit weight times h, where you measure, I guess you'd have to measure h positively downwards from this point. But you need to choose how you do it yourself, right? So that's for an incompressible fluid. So that's straightforward. Bless you. So this is where density equals constant. In other words, is not a function of pressure. And so for a compressible fluid, a gas, we can do the same calculation, and we can use the same expression. By the way, this expression is always correct. always correct, irrespective of the compressibility or lack of compressibility of the fluid. And so for this, dP over dz is equal to minus rho g. Just expanding what this is. This is the density of our liquid. And I suppose what we could do is look at the density of our liquid. We know that pressure absolute is equal to density times RT. We can rearrange that in terms of density being equal to pressure over the gas constant times temperature. This is absolute pressure and absolute temperature. I guess we should be aware of that. And so we could substitute that into this. So we could write this as change in pressure with elevation is equal to minus P over RT times G. And I suppose we could write that by gathering terms as dP over P, right? This term here and this term here, to get that on the same side. Put Z on the other side, so this is minus GZ over RT. Of course, it's not just Z, it's dZ, right? And we can do exactly the same. P1, P2, Z1, Z2 for this diagram. And if we do that, we end up with log P, P1, P2 equals G over RT times Z, Z2, Z1, hopefully. And so if we write that out in longhand, it would be P log P2 over P1. Not difficult math, you've seen this in elementary calculus. It would be G Z2 minus Z1. I think there's still a negative sign in there, right? Over RT. Absolute temperature, these are absolute pressures, still a minus sign. And I guess the only gymnastics you need to know is that E to the log X is equal to X. So if we exponentiate both sides, we get P2 over P1 equals exponential of minus G Z2 minus Z1 over RT. Bit of a long derivation, but not so onerous. And that's it. Well, that's not quite it. One final coup de grace. So multiply both sides by P1. So the pressure at point 2 is just equal to P1, both absolute pressures, times the exponential of minus gravity, not a very good G. The difference in elevation, Z2 minus Z1 over RT. And I'm reminded by my own notes that the gas constant is R is equal to 283 joules per kilogram per Kelvin. Joules per kilogram per Kelvin. And temperature, well, we're probably 20 degrees centigrade today, but we want it absolute. is about 293 Kelvin. And so the two expressions that I want to get out of today are this one. Don't need to derive these, but just so you know where that comes from, I thought we should go through that pain. Tell me if there's something wrong, if you're following me. And this one. Those are the two expressions. And of course, they're quite different. And I don't know whether, don't know how it's supposed. Yeah, you could imagine what they are. Perhaps it's good to just sketch exactly what they are. Actually, I've got it here. So the reason that my stuff wouldn't open is because I've got equatio here. And those two expressions are defined exactly here. So this top one is, yeah, you can see it quite well. This top one is P2 is equal to P1, atmospheric pressure at sea level, which is where we sit, minus Z times the unit weight of air times G. So this 1 times 9.81 is the unit weight. It's 1 kilogram per cubic meter times 9.81 meters per second squared. And so this expression, I guess it's not true for this, right? Because if we're using it for an incompressible fluid, it should be the unit weight of water, which is 1,000 kilograms per cubic meter. And it's a straight line. And it's this red straight line, which I'll draw out on the page a bit later. The other expression is that the pressure at point 2, P2, on your equation, is equal to P1 times the exponential of Z1 minus Z2. Z2 is always higher than Z1, so it's negative, times 9.81 times, can you see it? I don't know if it'll get any bigger if I do this. Oh yeah, it does on my screen. Times the ideal gas constant, which is 287 joules per kilogram per degree Kelvin, and the temperature, which is 293 centigrade. And so what you see here is that expression is this particular, the blue curve, which starts off here. So atmospheric is 100,000, so this is 100,000, 101,000 pascals. So that's where atmospheric pressure is at elevation Z equals 0. And as you go up from sea level, the pressure decreases until you get up to, this is 100,000, so this is 100 kilometers. So this is 20 kilometers, 40 kilometers, 60, etc. So where do planes fly? We said Everest is about 10 kilometers, so I guess it's half this. So the pressure on Everest is about 30% of the pressure that we feel here. So that's why you need oxygen, and that's why the little orange oxygen masks fall out if your window breaks on your plane, because you need to be able to breathe, because you only have 30% of the amount of oxygen that we have at sea level. And ultimately, by the time you've gone up to, is that 40 kilometers? So yeah, this is 10 kilometers, which is where planes fly and Everest is. Once you're at 40 kilometers, you're almost in space. So this means that above this point here, there's so little air above you being pulled down to the earth by gravity that you essentially feel no pressure. You're in a vacuum, because what we feel is just due to the fact that gravity plasters air on top of us. The red curve represents if now you land at sea level, splash down in the ocean, and now you go beyond the ocean as you go as a diver. So the unit weight of water is 1,000 kilograms per cubic meter. And so it's 1,000 times more dense than air, and it's incompressible. So this red line is a constant, but it goes down here, and you see it imperceptibly decrease. You can't see it because it's 1,000th of this gradient. And I guess I could probably try and move it. I'm not doing a very good job. I guess the problem is that I've both zoomed out my screen and I'm trying to zoom out this as well. Yeah, okay. So yeah, you can. So if I can't do it very well. So I want to pull this down. Can't do it. I want to get to 0. I'm going to draw it for you. I can draw a much better picture for you. So in other words, this goes down. So in other words, as you go down some very small amount in the water, say a meter, if you go down 1 meter, since the difference in densities of those fluids are the same, going 1 meter down below the surface of the water is the same as the pressure change you get for going 1,000 meters up because of the ratio 1,000 in the densities of the two fluids. And so it's easier for me to draw exactly what's going on. So if you want to draw exactly what's going on, then let's do that. So what I'm trying to draw is this. This is sea level. This is the vertical direction. I'm going to do another bounding line here in a gray. And I guess it was the blue curve. The blue curve you saw does this. And hits this, right? And the deal is that on this curve, if I blow it up, everywhere on this curve, should label my curves, right? So this is elevation. This is positive Z. This is negative Z. This is positive pressure. We know that dP dZ is equal to minus rho g over 1, which is minus unit weight over 1. And so then if this curve here, this is dz, this is dp, then if I draw another little triangle, then pressure is equivalent to unit weight. So I guess this pressure, I'm not going to do it on that curve. It's getting too crowded, and I'm doing too shitty a job on it. This pressure is right here. And so this pressure equivalates with this. So this is unit weight, and this is 1, right? Because this is unit weight in 1, pressure, and Z. Unit weight is equivalent to pressure. Elevation is equal to 1. And so this, as I said before, that dP dZ equals minus unit weight is always true. The gradient of this curve is always given by the unit weight everywhere. It's just that when you integrate this, it accounts for the fact that density is decreasing as you go further up in the column, so you have less and less weight above you, and if you're compressing due to that, you feel it. Below that, as you go below the groundwater, then this is the curve. This is exactly the same. I'll be able to do a better picture here. This is dz. Not good. This is dp, and therefore, perhaps you can see it better here. The gradient of this, which is constant, this is equal to the unit weight, in this case of water, and in this case 1. This would be the unit weight of air. And we need to make the distinction between what these pressures are. So this pressure here would be 101,000 pascals absolute, 0 pascals gauge, this point here, And this point here would be minus 101. I'll write it as kPa just for space, which is this one here. And it would, no, sorry, that's wrong, isn't it? You can correct me for that. Be 0, right? 0 kPa absolute and minus 101 gauge. So that's what it looks like. So absolutely rational for what we've talked about. We'll deal mostly with incompressible fluids. So often it will be this constant gradient, and you won't have to worry about the fact that you need to use this exponential, but it allows us to be able to determine exactly what's going in the atmosphere. Of course, one interesting question would be, how many molecules of air are in the atmosphere? Of course, you know that. You can calculate that because you know the pressure here on the Earth. You know that the mass above you must equal that weight of gas above you. You know the area of the Earth, and so if you multiply that area of the Earth by the mass above you, you have the mass of air, and then you can calculate from that, from the molar density of air, you can calculate the number of molecules. Be a cool thing to do. So that's it. That's all we've done. So it may look like smoke and mirrors, but if we kind of recap exactly what we've done, all we've done is we've said that we can look at a small cube of material, which is just like a bucket of material, but it has square sides, and some people don't like differentials for some reason. But it's basically saying that if you have a small cube of this material, which has a small cube above it and below it and around it on every side, we can treat that in some way to do a free body diagram to say something about the pressure, how the pressure varies with depth. And we get three equations out of it that represent us resolving both vertically, Fz, horizontally, Fx and Fy. And we get these three equations, which we can then use. In our simple case where the fluid is static, we can just get rid of these acceleration terms because we don't care. And as a result of that, it says something about the fact that we only need one equation, which is this expression. And if we do that, we can take two cases. Easy one is incompressible fluid. This equation here, we just need to be careful with our sign convention, with Z always positive upwards. You'll probably prefer to write it in terms of a height of stuff above you, which is just as fine, which is a much easier way to do it. And the result we get then is exactly the same as taking two buckets on top of each other, which we've got here. The more complicated case is if it's compressible, because each bucket of fluid is progressively less dense because it has less pressure acting on it, because it's compressible. And if we do that, we go through a simple manipulation, and we end up with a pressure at some point as we go upwards, diminishing according to this exponential, but it asymptotes to absolute zero pressure. Has to. Because once you get into space, you're in a vacuum, there's no air anymore, there's no air molecules above you, gas molecules above you, trace quantities of CO2, of course, these days, and therefore there's no pressure acting down on you. So that's it. Wonderful. Isn't it great? Also logical. I like it. Don't know if you like it, but I like it. Questions? Yeah.
What's the difference between absolute and gauge again?
It's just offset by this 101. So absolute pressure is what you have to use if you use the ideal gas law, because that's the way that the ideal gas law is defined. It's important to remember that. And so they just use a different metric. We drew this diagram, I think, on the second class that says if you look at pressure, and if you look at absolute, and if you look at gauge, then absolute pressure when there's no pressure is equal to 0. And if at atmospheric pressure, where we find ourselves, this is a vacuum. So absolute pressure in a vacuum is 0. In an atmospheric pressure is 101 kPa. An atmospheric pressure at gauge is 0, and this is 101 minus kPa. So it's just the scales are offset. So it's because if you have a pressure transducer on Earth, it measures the displacement of a diaphragm. And it's got the same atmospheric pressure inside it as is outside it. And so there's no deflection of that diaphragm when you calibrate it. And so, yeah, that's basically the reason. So, okay? They're just offset scales, that's all. Good question. Next time, I'm not sure what we talk about. Okay, so the good thing is that if you look through the notes that are after this, this is the math we didn't do today. So you can count yourself lucky. So these are yeah, fine. So next time we'll talk about manometry. So we'll talk about how you measure pressures at a point. And we measure them by pressure gauges, we measure them by columns of liquid, we measure them by manometers, and so we'll talk about that. Great. Have a fantastic Monday, and right on time.